One special case of Ito's lemma that comes up quite a lot is where you just have a function of a Brownian motion. We do that so frequently that it's worth writing this down separately. What if you have a yt that is just a function of some wt, which is a Brownian motion, and perhaps also separately a function of time? Brownian motion, remember, is the Ito diffusion with drift 0 and speed 1. So it's a special case of the Ito's lemma that I just wrote down before. So then Ito's lemma would tell you in that case, that yt is an Ito diffusion, and it can be described by this equation. dyt is ft dt for the dependence on t, plus fw dwt. This thing fw is the derivative of f with respect to its second variable, so it's the same thing that I called f sub x before, but now that the second variable is called w instead of x, I'm going to change the notation for the partial derivative as well. It's still the same thing though, it's just a different way of writing it. Plus, and now we get this third term that involves a second derivative, half times fww dwt squared. And this thing, dwt squared, what's that? That is another way of writing this. Increment in the quadratic variation, and since the quadratic variation of Brownian motion, if we look back to what that was, the quadratic variation of a Brownian motion between times 0 and t is t. So in fact, when we write this, what we have there is just dt. So the upshot of it is that where you see the symbol dwt squared, you can remember that's just the same thing as dt. Therefore, this third term in our Ito's lemma thing, that's just another dt, which means we could combine it with this other term. So what we finally get for that case is two terms that involve dt, plus that term. So yt is an Ito diffusion, its speed is this thing, this partial derivative, and its drift is the sum of these two terms. I'll even combine them. That's the drift, that's the speed, and notice also that this dwt here, this is the same w we've been using all along. So this says that the internal w, the internal Brownian motion of y that helps you to explain the drift and speed of y, is the same one that you first thought of. Alright, it's past time for an example. I am going to do a derivation of Ito's lemma, but I'll put that in a different video. For now, let's concentrate on this example. Wt, a Brownian motion, we'll take it to the fourth power. If you take a Brownian motion to the fourth power, what do you get? Well, according to Ito's lemma, you get another Ito diffusion. Brownian motion is the Ito diffusion with drift 0 and speed 1. Brownian motion to the fourth power is an Ito diffusion with some drift and speed, and now that we've got Ito's lemma, we can work out what they are. So just to remind you, this has the form f of twt, where let's explicitly write down what the function f is. f of t and w is w to the power 4. See, I'm writing it here as just a function, so I've put just a variable here. Just lowercase w is just a variable that I'm using to tell you what the function is. You take that variable to the 4th power. And then in this expression, we've got the Brownian motion value plugged in for that w variable. Okay, so we don't need to worry about the partial derivative with respect to t, because that is going to be 0. Partial with respect to w is going to be 4w cubed. And the partial with respect to w twice is going to be 12w squared. So what does Ito's lemma give us? That'll be, ignoring the partial with respect to t term, which is 0, we've got a partial with respect to w, so that's 4wt cubed. Remember, when we write the partial derivatives, they have to have the appropriate random variable plugged in, even though we don't normally write that, so that's 4wt cubed dwt plus a half of this, the second partial derivative, again with the random variable plugged in, dt. This, remember, is the term that in general would be the quadratic variation, but in the case of a Brownian motion, the quadratic variation is just t, so we just get another dt there. So, great, we can immediately see what the drift and speed of xt is. What's the drift and speed of a Brownian motion to the 4th power? Its drift is 6wt squared, which is always a positive quantity, so 4th power of a Brownian motion is always drifting upwards, which sort of makes sense because it's a positive quantity itself and it starts out being 0, so there's only one direction it can go. And its speed is 4wt cubed, which tells you that the bigger wt gets, either positive or negative, the more volatile the 4th power of it will get, the bigger the local variance of its increments will get, which also makes sense because if you take the 4th power of something big, you get something that is not only big itself, but is very sensitive to small changes in that input. In fact, the sensitivity of it is 4w cubed, the derivative. This is it all written down in terms of dx's and dw's, but if we wanted it back as in forms of integrals, let's just write it that way, just to remind ourselves. The xt would be the starting value plus this. That's a stochastic integral coming from that term, plus that, and that's an ordinary integral coming from that term. Xt, remember, is wt cubed, and x0 is 0. So if we rearrange that a bit, what will that tell us? That we can use that now to figure out what this stochastic integral is. So what this tells us is that this stochastic integral, the integral of w cubed dw, can be expressed like this in terms of just a function of the final value of the Brownian motion, wt, and an ordinary integral involving w. So this is one way that you can think of working out what stochastic integrals are. If you remember back to when we did the integral of just w dw, we found it was a half wt squared minus t. We did that kind of by brute force, by actually taking the limits of sums, but that's not a very practical method most of the time. Ito's lemma gives us a better way to do these things. We can work out integrals like this, or at least reduce them to other integrals by using Ito's lemma. As another example along similar lines, we could consider this one, the integral of e to the w dw, and reduce that to what it says over here. Always nice to be given the answer to aim for. So in this case we would take, let's call it yt this time. E to the wt seems to be the important function. We've got that coming up here. We've got an e to the wt minus 1, which looks like a yt minus a y0. So that has the required form. It's f of t wt, where f, remember, is just a function. It can only be just a function. That's what f is. So according to Ito's lemma, dyt would be, let's write it out in full here, again, there's no partial with respect to t to worry about, so second term, take the partial with respect to w. Well, this is easy. The nice thing about the exponential function is that no matter how many times you differentiate it, you always just get itself. So for fw, we just have e to the wt again. And for fww, we just have e to the wt again. That's Ito's lemma, or put that into integral form. Yt minus y0 would be from that term, and from the other term we get an ordinary integral. And now it's just a matter of rearranging things a bit to get the required result. Yt, remember, is just e to the wt. So this is y0 is 1, not 0, and yt is e to the wt, so that's minus this other bit.